about, of course, anti-serum, this polyclonal mix of antibodies in your serum that are made towards all these epitopes. Great for passive immunity, neutralizing toxins, kind of a prophylactic use as well. But vaccines, on the other hand, are a little bit different. And one of the cool things about vaccines, of course, is that we get this immune, or what we call herd response, or herd immune response. And it's not that we're trying to specifically protect you individually, but we're trying to protect large populations at one time, usually. So even though it's an individual thing, true vaccines are really targeting populations. Whatever your vaccine might be made out of course, it's got to elicit a strong immune response. And we're thinking particularly about those antibody-producing plasma cells. You're also hoping that you'll get some of those memory B cells out of that as well. So think back again to when we talked last time about the primary and secondary antibody response to an antigen. How with that secondary response we get that class change to IgG, and we kind of get that boost. So most all of them need some sort of booster. And so when we're talking about boosters in this effect, think of it as that secondary exposure to whatever pathogen or antigen that we're using for the vaccine. So with this, we can make vaccines out of a whole bunch of different things. Whole pathogens. These can be dead or alive. I think it's going somewhere else. I'm going to cross my fingers. It can be parts of a pathogen, so we call these macromolecules. And just think of proteins, carbohydrates, and lipids as being great vaccination precursors. And then, of course, we can utilize toxins like exotoxins, etc. So now, most of the time when we're talking about macromolecule vaccines, we get them in a few different ways. And so we'll kind of talk about how we end up getting various types of vaccines. So we'll talk about these macromolecule first. And then we'll come back to those whole organisms, whether they're dead or alive. And so for our macromolecules, the ones that make really nice vaccines are ones that are going to elicit the biggest response. So if you think back to what an antigen must look like, it has to be big enough. It has to have those two distinct features or epitopes so that your immune system recognizes it. And the big ones that we utilize, of course, are proteins, lipids, carbohydrates, etc. And so most of our toxins are protein toxins, so those toxins would be ranked under the proteins as well. So we'll start with proteins. We get proteins in a couple of different ways. And a large portion of the vaccinations we get out there are protein vaccinations. And we can develop these protein vaccinations either by one, purifying from the pathogen itself. That means you have to break the pathogen up, isolate the protein, purify it down. We do that, but it results in very low yields and is very time consuming. So what we do more or less nowadays is called recombinant protein vaccinations. And so what we end up doing is we put the protein, or the gene for the protein, excuse me, into E. coli. That E. coli can just produce a mass amount of it in a beaker. Very easy to amplify and produce. Much easier to purify from all that other cell debris when you're just trying to get it from the pathogen. And you get large amounts this way. Works out pretty well. Then of course for your lipids and carbohydrates, we need to more or less get these from the pathogens themselves. It's much harder to get genes for those macromolecules to give us recombinant. So for your other macromolecules, we also have to purify those from the pathogen like we do some of the proteins. And so, as we see with most of our vaccinations, hopefully we're getting some sort of antibody response. So, usually we get a measurable response. Usually 7 to 10 days after your primary exposure, that first exposure. We see generally an increase for another about 2 weeks or so. And this continues on until about the 1 year mark. Give or take. And then it just stays at what we can call constitutive levels. And then it will slowly decline after a period of time. Of course, this is where we usually see this booster. And we usually think of giving that booster somewhere like 4 to 6, 4 to 8 weeks after the primary vaccine or the primary exposure. And that's when we see that class shift, and we bump an increase in all of that. Works well for all these macromolecules, but it works even better when we deal with live organisms. So I know this is kind of a strange concept, but we use it all the time. And has kind of led into the autism debate. So even though these macromolecules work really well, they do kind of have their limits. So for instance, if you utilized a protein toxin as your vaccine, let's just say the tetanus toxin, it doesn't elicit a very strong response. So what, every 5 to 7 years, you're supposed to get a new tetanus shot, a new tetanus vaccine for that toxin. So for certain proteins and macromolecules, it's not a very strong response. But anytime we can get some live organism in your body, you produce these really strong responses. And that's why these live attenuated vaccines work really well. So we see longer immunity and an increase in antibody concentration, or the number of antibodies produced. And this is compared to killed cells or macromolecules or pretty much any other vaccine. These